Hello and welcome to a presentation on scalable data transportation and ingestion with MemQ. My name is Ambud Sharma. I'm a tech lead at Pinterest, and Pinterest is the home of inspiration. In order to inspire our users, we use machine learning. And in order to power machine learning, we collect large quantities of ML training data. This is what a typical data ingestion and transportation layer looks like. We have systems that generate data and systems that transport data, including the upstream, ingress, pub/sub layer, egress, and downstream. At Pinterest, there are three use case families that are powered using data ingestion and transportation platform: analytics, replication, asynchronous communication. The analytics use cases are typically the clickstreams type use cases: product analytics, ads revenue reporting, signal platform, machine learning, so on. Replication typically refers to our cross AZ, cross region transports of data, and also database write-ahead logs. And asynchronous communication is typically applications communicating with other apps using asynchronous medium or the pub/sub layer. This is what the data transportation architecture at Pinterest looks like. We have several managed services, including our clients, our agents, on both ingress and egress side. And we have hundreds of applications using this platform. Today, we're going to talk about the MemQ-based machine learning data transportation platform. So at Pinterest, we have two primary challenges with machine learning data transportation. First is scalability. Machine learning teams keep adding more data for training more use cases. And these changes can be ad hoc or very spiky in nature when they're enabling and disabling features. And then the second part is the cost that comes along with large scale machine learning collection. We have petabyte of data being captured per day, and transporting that data is expensive. So why MemQ? Well, running custom application in the cloud is expensive. And specifically, sub-second latency is not necessary for certain analytics use cases, like machine learning log collection. Storage and serving also need to be separated in order to enable scalability for the pub/sub environment. And strict write ordering is not necessary when it comes to machine learning training for batch training use cases. Again, ordering on reads is something that provides customers and applications more flexibility, because most of the cases at Pinterest, they're ordering by timestamp of different cases. For example, ingestion timestamp or device timestamp, in which case ordering on write is completely irrelevant. And lastly, Apache Kafka rebalancing is very expensive, which is what had been powering the platform in the past. So what is MemQ? MemQ is a scalable pub/sub system with a pluggable storage engine. It relies on an external storage engine like Amazon S3 or HDFS for replicated storage, and supports fire and forget, acknowledgement by the broker, or acknowledgement by the storage layer as the several acknowledgement semantics. It uses a packet or batch-based storage system that enables it to scale. MemQ has the following components. It has producer, consumer, the broker, the storage layer, the notification system, and the governor, which is used for clustering. So let's see how MemQ works. On the producer layer, applications are generating data, which is then aggregated by the producer into what is called a MemQ message, which is then sent to the TCP handler and the API layer, and finally ends up in the topic processor for the given topic. The topic processor then further aggregates the data from multiple producers and creates what is called a MemQ batch. The MemQ batch is then sent to the storage handler, and the storage handler then persists the data on the storage layer, in this case Amazon S3, and the notification system to send a metadata update to the consumer. If acknowledgements are enabled, then an acknowledgement message is sent back to the producer. And then on the consumer side, the notification message is consumed first, and then the consumer reaches out to the storage layer and posts the actual data. So let's talk about MemQ acknowledgement model. Because we're using an object store like Amazon S3, we had to create an asynchronous acknowledgement protocol. This was necessary to hide the latency that comes associated with a system like Amazon S3. And also, we needed to increase the throughput so that we could aggregate as much data as possible before dispatching it to the storage layer. It also helped us improve our compression ratios. Let's talk about the MemQ storage internals. Well, MemQ has a tiered storage internal and it has a packet-based storage protocol. What that allows us to do is batch data at different layers and persist that onto the storage layer. We have at the top level, which is the actual object called the MemQ batch. Underneath that, there are one or more MemQ messages. And finally, the applications are sending log messages, which are aggregated underneath the message. The features of this format are optimized compression because we're using larger batches of data. We can reduce memory footprint because we only need to decompress the data that is currently being processed. We can provide the flexibility of batch versus streaming workload because people can consume the data either in batch quantities, like large scale scans, versus streaming, which is continuously processing data. And lastly, we're not making any assumptions about the underlying storage system. For example, that page cache is available or that data exists in memory. So why should we be using a batch or packet-based storage layer? Well, first, log data is immutable. Example, machine learning training data that we have. That allows us to handle infrastructure failures and re-replicate only the data that is necessary to be re-replicated in the case of lost data. Throughput and latency control is another aspect. Well, because we have batches, we can control how big these batches are and allows us very fine-tuned control about on the latency. We can also separate storage and serving layers because the machines that are serving the current writes don't need to be the machines that are currently serving reads. So we can round robin and use different hardware to be able to scale out reads and writes separately. Efficient batching and streaming is also enabled using this. And the reason is because we can actually consume batches of data all simultaneously, given that the underlying storage layer, for example, in this case, is Amazon S3. We're also able to leverage object stores or any other file system for that matter, as long as it can take writes on a file or object by object level. And lastly, cloud providers are using economies of scale to optimize storage, and we're able to leverage that out of the box. Let's see how MemQ and Apache Kafka scalability compare. Well, MemQ, since it leverages Amazon S3 as a replication system, can handle 1:1 traffic. Whereas in the case of Apache Kafka, every broker can only handle a third of the traffic because it has to have capacity to be able to handle replication requirements. MemQ also is able to have disk scaling automatically because it's using Amazon S3 as a replicated storage engine. In the case of Apache Kafka, we have to maintain and manage those machines ourselves. The trade-off here with MemQ is MemQ has to have higher latencies because it's using Amazon S3 as storage versus Apache Kafka, which can sustain sub-second latency. How does MemQ compare to Apache Kafka when it comes to features? MemQ enables acknowledgements by default. It enables app all by default. And that's to reduce the probability of data loss. Kafka, on the other hand, does not support app all by default. You can enable that in Kafka, but it is more expensive. Ordered production in MemQ is not supported because, as I mentioned before, analytics use cases, especially in the case of machine learning training, do not require ordering. And lastly, MemQ does not support transactions because, once again, analytics and training use cases do not require transactions. So how did we make MemQ happen? What are the optimizations we did? We reduced several copies of the data that were originally existent in memory to allow us to reduce our garbage collection. This was done both on the client and the server side. And on the server side, we were able to get effective zero garbage collection. We also did several contention optimization by salting of the write paths that enabled us to reduce latencies and on Amazon S3. And we also did speculative uploads that allowed us to counter long tail latencies that we see on Amazon S3. So where are we at with MemQ? Well, I'm proud to say that MemQ currently powers all machine learning training data at interest. It's able to handle spikes of up to 2x without expensive rebalancing and save over 80% cost over Kafka for machine learning data transportation. We also were able to build a low latency version of MemQ with P100 latencies of less than 10 seconds. What's next for MemQ? Well, we're trying to roll out MemQ low latency to several use cases and perform Flink integration so that real-time processing can also be performed. And lastly, we're trying to do streaming and bash integration using unified SQL layer. What are the highlights out of this? Well, we reduced our cost for ML machine learning data transportation by 80%, enabled large-scale ML training ingestion by allowing more experiments from application teams and being able to use higher sampling rates for capturing training data. When comparing MemQ to Kafka, it's like comparing a freight train to a sports car. You use a freight train to transport cargo, not a sports car. MemQ is able to save over 90% cost over Apache Kafka while transporting data. All right, so what are the takeaways out of MemQ? Well, we were able to establish that cloud-native systems are efficient and more scalable. And we are able to use decoupled storage and serving and inexpensive cloud-replicated storage to service our needs. Next, relaxing constraints in distributed systems, specifically ordering constraints, helped us open architectural options to be able to increase our throughput, scalability, and reduce cost. And lastly, cost math matters. We used our cost-based equations to figure out what the batch sizes, request rates, and other parameters in MemQ should be. Also, there should be a premium for low latency, and that's what MemQ is leveraging. We are able to showcase that higher latency systems shouldn't nearly be as expensive as lower latency systems. And we're happy to announce that MemQ is open source. You can download MemQ at github.com/pinterest/memq. Thank you.